Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book, Retrolinear. The subject of this lecture is complex numbers and thinking of them as a vector space and also as a field. I have several videos on various mathematical objects that are examples of vector spaces as a way of introducing you to what a vector space might be before we start a formal study of vector spaces. R is the set of real numbers, things like -3, 4/47, square root of 11, pi, e, and so on. C is the set of complex numbers, and that's the set of numbers of the form a plus bi, where a and b are real numbers and I squared is -1. When I write a set notation like this, a plus bi, these are the elements of my set, and this vertical line such that is going to tell me conditions about that. So a and b are going to be real numbers, and I has the property that if you square it, you get -1. And these are things like -3 plus 47i, 2 plus pi I, -3 is also a complex number because a could be -3 and b could be 0, and so on. Whenever you put a real number plus another real number times I, you get a complex number. Now, the first question that a lot of students ask is that, are these actually numbers? Is I really a number? Do we have a number that when you square it, you get -1? There's no real number like that, and in that way, I is not really a number. But the question is that, are there any numbers like that real or not? And to answer that, you first have to actually ask, what is a number? If you are going to ask whether I is really a number or not, you have to ask what a number is. And that definition has evolved over time, and in fact, has become more inclusive and included more things over the centuries. Originally, the numbers that people thought of a number were the counting numbers, 1, 2, 3, 4, 5, 6, and so forth. It took a while before people thought about rational numbers also as numbers. Egyptians, for example, started out with unit fractions, things like 1/3, 1/5, and also 2/3. They only used unit fractions. But over time, other fractions were included in the set of numbers as well. Later on, negative numbers. A little bit later on, 0 was included as a number. And eventually, the real numbers, things like square root of 2 and pi and e, were included as numbers. And that was actually a big advance, one that opened the way for developing calculus. So the question really isn't what is a number. The definition of a number has changed over time. What really matters is that if you have a collection of objects, can you really treat them as numbers? Do they behave as numbers? Can you use the same rules of numbers for adding, subtracting, multiplying, and so on as you do for the other numbers you had? And is that a useful thing to do? And the answer for all of these things for complex numbers is yes and yes. You can treat them as numbers, they behave like numbers, and they're very useful. In mathematics and physics, C is the set of complex numbers, and again, it's the numbers of the form a plus bi, where a and b are real numbers, and I is a number that when you square, you get -1. Every element in C is a complex number. One way we think about this is we place them in the plane. These points on the plane are all going to be complex numbers. On the x-axis are the real numbers, so there's 1, there's 4, as you might expect. On the y-axis are pure imaginary numbers. So for example, I is up there. And then there are other numbers like 3 plus 2i. You go 3 on the x-axis and 2 units up the y-axis, you get 3 plus 2i. -2 plus i is over there. -1 minus i is here. And 3 minus 2i is just the reflection of 3 plus 2i about the x-axis. And that's called the conjugate of 3 plus 2i. I want to think of C as a vector space over R. Whether or not you know what a vector space is irrelevant, but vector spaces are sets of elements where you can do addition and scalar multiplication. Those are the games you can play. You have to be able to do addition, scalar multiplication, and they have to follow certain rules. We can add complex numbers. For example, if you take 3 plus 2i and -1 plus 4i, you add like terms. You add the real number, the 3 and -1, and you also add the I part. So you get 3 minus 1 is 2, 2i plus 4i is 6i. So this complex number plus that complex number gave us a new number. And you can multiply by scalars. 4 times 1 minus I is 4 minus 4i. Scalars right now for our first go-through are real numbers. When I say a vector space over R, the scalars are real numbers. Can they be something else? Yes, they can be. And we will talk about briefly at the end, but in other videos in much more detail. And addition and scalar multiplication have to follow the vector space rules. And because of that, we say that C is a vector space over R. When we say over R, that just means that the scalars are real numbers. And being a vector space means that you have an addition and scalar multiplication and they follow certain rules. The rules are silly, actually, but but they happen to be quite profound, much more than you think they are. Whenever you have a vector space, the elements of that set are called vectors. So in this case, the vectors are complex numbers. Complex numbers are actually vectors, and the scalars are real numbers, as I've been saying. C is a vector space over R. It has addition and scalar multiplication, and they follow the rules of a vector space. What are those rules? Here are the rules. If you add two complex numbers, the addition is commutative, the addition is associative, x plus y plus z is x plus y plus z. Note that each one of them is something of the form a plus bi. There is the number 0, the 0 plus 0i, and that's the 0 of this vector space, because when you add it to other elements, nothing happens. And every element has an additive inverse. There's some other element that if you add to it, you get 0. A plus bi, its additive inverse is minus a minus bi. If you add those two things, you get the number 0. And there are properties of scalar multiplication. If you take any scalar alpha and multiply it by the sum of two complex numbers, you can distribute that in. Alpha times x plus y is alpha x plus alpha y. Alpha plus beta times x is alpha x plus beta x. Alpha beta times x is the same as alpha times beta x. And finally, the silliest of all, 1 times x is x. If you take the number 1 and multiply by a complex number, nothing happens. These are the properties that complex numbers share with other vector spaces, with Rn, with polynomials, with matrices, with functions. And that's what makes it a vector space. The fact that you can add and you can multiply by scalars, and they follow these rules. If you haven't actually gone through linear algebra and don't know what a basis is, what linear independence and spanning is, this is just to whet your appetite. Again, the complex numbers is the set of all the elements of the form a plus bi, where a and b are real, and I squared is minus 1. Two of those elements are 1 and I. Those are two elements in this complex set. And we can't multiply 1 by a scalar to get I. The scalars are real numbers. If you multiply 1 by real numbers, you get other real numbers. You never get I. And that tells us that 1 and I are linearly independent over R. That means that using scalars from R, I can't get one from the other. For more precise definition, watch my videos on linear independence. It's also true that a general element, a generic element of this vector space, a plus bi, can be written as a times 1 plus b times I. This is called the linear combination of 1 and I. Another way of saying that is that 1 and I span C over R, using scalars from R by finding linear combinations. By multiplying one of these by a constant and another one by constant and adding them, I can get every element in this vector space. That means that this 1 and I is a basis for this vector space. A basis is a set of elements in a vector space that's both linearly independent and spans. When you have a basis, the size of that basis, the number of elements in that basis, is called the dimension. And for that reason, C is a two-dimensional vector space over R, and we write that as dimension of C over R is 2. The over R part is always telling us what the scalars are. The complex number are actually more than a vector space. They are a field, and I want to explain that. We can actually multiply complex numbers. Now, in a general vector space, we don't do that. Elements of Rn, we don't multiply them and get other elements of Rn, for example. But we can multiply complex numbers. For example, 3 minus I times 2 plus 5i. How do I multiply? 3 times 2 is 6. 3 times 5i is 15i, minus 2 times I is minus 2i, minus I times plus 5i is minus 5i squared. But remember, I squared is minus 1. That becomes plus 5. 6 plus 5 is 11. 15i minus 2i is 13i, so I get 11 plus 13i. I can also divide complex numbers by non-zero complex numbers. If you look at 3 minus I over 2 plus 5i, that actually doesn't look like a complex number, because again, a complex number is a real number plus another real number times I. This is not at that form. The trick is to multiply top and bottom by the conjugate of the bottom. So that's 2 plus 5i was in the denominator. We multiply top and bottom by 2 minus 5i. The advantage of that is that down here we have a plus b times a minus b, and that becomes a squared minus b squared. Now, a squared is going to be 4, b squared is going to be 25 I squared, and I squared is minus 1, so that becomes minus 25, and 4 plus 25 is 29. And the upstairs, if you multiply it, you get 1 minus 17i, and then you can separate it out into 1 over 29 minus 17 over 29i, and that is a complex number of the form we like. It's a real number plus another real number times I. In the complex numbers, not only we have addition and subtraction, we have multiplication and division by non-zero numbers. And whenever you have that, whenever you're in a set of non-empty set of elements where you can add, you can subtract, you can multiply, and you can divide by non-zero elements, we call that in mathematics a field. And a field are the scalars for a vector space. So what do I mean by that? In the first run through linear algebra, the scalars are always real numbers. But as you get more sophisticated, the scalars can be elements of any field. What's a field? A place where you can add, you can subtract, you can multiply, and you can multiply by non-zero elements. And C is a field, and therefore it can act like the scalars for a vector space. You can have vector spaces where the scalars are complex numbers, and that actually end up being very important. Here are some examples for vector spaces over complexes where the scalars are complex numbers. If this is your first run through linear algebra, you can just ignore these. Just like R2 is a vector space over R, C2, pairs of complex numbers, is a vector space over the complexes. This X and Y are elements of the complexes, so each one of those is something like 2 plus 3i and 5 minus 8i. And all of those together form a vector space. Polynomials with coefficients in complex numbers, those form vector spaces. Matrices, n by m matrices with entries in complexes, those also form vector spaces over the complexes. And as in the final example, C itself is a vector space over C. We had seen that C was a vector space over R, but it's also a vector space over C. You can think of the complexes themselves as being the scalars for C. In that case, 1 alone is just the basis for C, because using 1, you can multiply by scalars. Now the scalars are complex numbers. So for example, you can multiply 1 by I and get I. And by just multiplying 1 by scalars, you can get all of C, and therefore the dimension of the complexes over complexes is 1. The dimension of complexes over the reals was 2, but over complexes is 1. Now this is the end of this lecture. Like my video if you liked it. Subscribe to my videos if you like to be subjected to more math videos, and keep hydrated at all times. I will see you at the next lecture.